Good afternoon, everyone. This is Stuart Stow. I'm the Director with the Homeland Defense and Security Information Analysis Center. Thank you for joining us today. I'd like everyone to know that we'll be recording the webinar. The slides will be available for download through the platform itself, and the full presentation will be available tomorrow for download on the HDIAC website. For any questions that you may have during the webinar, please write them down in the chat box that you see in the upper right-hand corner, and we will address them at the conclusion of the presentation. Before we get started, I'd like to do a brief overview of HDIAC, our center, and how we support the Department of Defense. We're one of 3 Department of Defense Information Analysis Centers with the headquarters located at Fort Belvoir in Virginia. We support the research and development as well as the scientific and technical needs across the 8 focus areas that you see on the right-hand side of this slide. We do that in a variety of ways, including research and development, scientific and technical information, resources that are available to our user community. That includes within the Homeland Defense and Security, as well as in each of the areas that you see, again, right there on the right-hand side. Next slide. In addition to our in-house subject matter experts, we also have a vast volunteer subject matter expert network. They support the Department of Defense through our center in authoring journals, spotlights. They help present our webinars like the one you see today, contribute to Tech Talks, as well as a bunch of our other service offerings and products. If you're interested in joining our network, please visit hdiac.org, or you can use the email that's at the bottom of the slide there. We're very excited to introduce today's presenter, Dr. William Kennedy. Dr. Kennedy has had a distinguished career, retiring after 30 years in the U.S. Navy. Additionally, he has worked in both the Nuclear Regulatory Commission and Department of Energy. Dr. Kennedy currently works as an associate professor at George Mason University, providing expertise on modeling cognitive processes and modeling human behavior in agent-based models of groups and societies. Dr. Kennedy, thank you for joining us. I'll turn it over to you.
Thank you very much. I appreciate it, and I appreciate your efforts in making this communication process possible. So what I'm going to talk about is the status of a basic research project that the DTRA, Defense Threat Reduction Agency, is supporting with me and George Mason University. And the basic outline of what I'll talk about is the big questions that we're researching, some challenges that we've had with the resources for this project, and the steps that we've gone through to generate a synthetic population and model routine behavior, and then to add in the nuclear weapons effects and initial reaction by the subjects, the humans, and then how we characterize the population's reaction. Also working into that discussion of agent-based models as a methodology for studying this kind of a question, and then where we've talked about this in other places and what our current plans are. So moving on to the next slide. Okay, this is the normal, mandatory, common quad chart. The basic objective is for us to characterize the reaction of the population of a megacity to a nuclear WMD event. It was originally considered that we would look at a reaction to a megacity outside the United States, and we decided that that was not politically correct, and so we are looking at a megacity in the United States. In the United States, there are only 2 megacities. The definition of a megacity is a population over 10 million, and the only 2 that we have in the U.S. are New York City and L.A., and they are very different cities in nature. New York is vertical, concentrated on an island, and LA is horizontal and distributed and doesn't have anywhere near as many high rises and tall office buildings. So we selected New York as a subject to study. The methodology that we're using is an agent-based model at a scale of 1 to 1. We have 1 agent in the model for each individual in the New York city area, which is approximately 23 million people, and we're aiming to model them at the one-to-one level. The significance of an agent-based modeling approach is that you model the things of interest and see how they aggregate up to the higher levels. So rather than monitoring a GDP or a average consensus of the people that are being the subject of the investigation, we are modeling the individuals and then add up what they actually do. It allows us to see the transitory nature of an equilibrium or whatever evolves or emerges from the large number of agents interacting. And it becomes complex when the agents, in fact, interact. We do not have the mathematics to represent their behaviors in a closed form, and so what we can do is simulate. So that's what we've been after. It's originally a 3-year project. We've been extended for an additional 2 years. And is there anything else in here? The other thing of significance that I would point out is that the funding profile is relatively small for a research effort. It's only $150K per year, and that means I don't have a large team of people working on this. I've got a couple of grad students and a couple of faculty members. Okay, moving to the next slide. Again, I've mentioned that the purpose of the goal of this research is to characterize the reaction. And I'll describe some of those terms as we go along. So the nature of the task. Modeling people is not easy. If it was easy, we would have nice closed form mathematical representations, and we could calculate it and hopefully come up with very nice thumb rules of general reactions. And we all have those from our own personal interactions, but to collect all these people and make sense out of it, we're building a model of the individuals themselves. And to compare this to, quote, hard sciences, since social science is typically not considered a hard science, and making it a computational social science isn't always accepted as a hard science, and it is clearly an experimental science. I have a couple of nice quotes. And I got to press the right buttons to get to come up. Okay. Murray Gell-Mann, Nobel Prize in Physics, commented on how hard it would be to model, how far physics would have gotten if the electrons themselves could think. Murray Gell-Mann was part of the founding of the Center for Social Complexity and the center here, the Krasnow Institute at George Mason University, that studies complex social interactions. And Murray Gell-Mann's quote doesn't stand by itself. Another character from physics history, in the form of Richard Feynman, also commented on this topic. And you can read the quote, but it basically says it's one thing to model electrons, and it's another thing to model rational electrons, and now what if they become emotional and had feelings? It gets even worse. So we're going to try to represent our agents and put in both their rational rule-based behavior and some irrational behavior and see how it plays out in our simulation. So it makes it a much more interesting challenge, partly why I'm interested in it. Okay. So where we are, big picture, we're about 3 years and a quarter into this project. It's basic research. We are advancing the science and publishing as we go to further the science able to support these kinds of projects. In the first year, we studied disasters, starting with the Halifax explosion in 1917, in which a munitions ship blew up in the harbor, and it was approximately a little less than a 3 kiloton explosion. And it was one of the first disasters that was studied scientifically and was produced a PhD from Yale University in 1920. But there have been lots of other disasters where we can study how people have reacted and how we can go about modeling that. And luckily, there's only been 2 nuclear weapons events that we can study how people reacted, and we have quite a bit of that information and have read those stories. In the first year, we also developed some pilot models to see how this would play out and worry about scaling. In the second year, we talked about scaling. We explored scaling up from small numbers of agents to larger numbers and saw how that is going to be difficult. And we made our first runs demonstrating routine behavior. And in the third year, which we just finished at the end of May, we had explored and characterized the beginnings of a reaction to a nuclear WMD event. In the fourth and fifth year, we're refining and enhancing the modeling, trying to improve the fidelity of our agents and their behaviors and the range of their behaviors so that we can get a better description, better characterization of their overall reaction. Moving on, our model consists of representing the physical environment of the New York City area. We're not modeling in 3 dimensions, we're only modeling in 2. But we have to deal with the roads, the physical environment, the buildings, the subways, the waterways, etc. And those things are represented in the model. We also deal with the individual that I described. The individuals are synthesized based on the 2010 census, and I'll spend a little bit more time on that in a couple more slides, and then how the agents interact in their work environments, in their home environment, in schools and daycares and other group activities. So we build the model in layers, the physical layer, and we add it up to produce the overall environment for our agents to operate in and then collect information. And so we've got lots of layers of information to represent and interact with. Okay. This is an image of the New York City area and the region around it. It involves several parts of several states. We include all the way to Rhode Island and a little bit of Pennsylvania on the east and west. We stay with New York and Connecticut going north, and we go down into New Jersey. And the gray lines on this are roads. And just the density of the roads gives you an idea of the density of the people that we are modeling. And the significance of the road that's where our agents are going to be moving. So we needed to be able to produce that and connect it. You would think that because we're able to drive our cars with their automatic navigation systems advising us, that all those road systems would be connected. But when we started this project, the public sources that we had for information did not have all those road systems connected. They were off by a couple of meters, tens of meters, but that meant that our agents who were following the rules could not navigate, and we had to struggle to make that work. So to describe the efforts that we put into this, we've had a resource challenge all along. Our sponsor acknowledges that, and we're working around it. Our project produces valuable students. We have literally lost a student to a startup in Silicon Valley, and hopefully he will finish his dissertation, but we lost him at the end of the first year. We also lost a student. We've had some turnover, obviously. We've also lost a student because the project is too much fun and you get pulled into it and spend too much of your time considering that you have other priorities as students, like graduating and having a life. And so we lost a student to a new marriage and trying to finish her PhD. makes perfectly good sense. And so we've addressed that within our budget by recruiting volunteers. And we've been relatively successful with that. And we brought in some Air Force Academy cadets who were majoring in behavioral sciences, and they joined us a year ago and spent their summer with us and contributed to our project. And I've engaged, a couple of high school students who contributed to the computer science part and to the emergency first responders information that we were using. So we're expanding our resources. I recruited an undergraduate here at George Mason who was in my class and commented that she only had one class to go to graduate, and I said, "So you're not busy?" And she accepted that and joined our project, and then joined the graduate program here and is now actually working on the project. So that student became a full-time graduate student and became part of our project. So let me describe what we've been working on. So first we had to synthesize the population and then try to get to their routine behavior. So the basic process that we went through was to first connect the roads. We started with a road network to provide a skeleton to place our agents on in the environment. So we had to create a topology, try to get all of our roads connected, not have little islands of roads where people couldn't get anywhere if they stayed on the roads. And that took a while playing with how large an approximation you allow to connect roads together. A meter doesn't seem too difficult. Maybe 10 meters is too many to consider that they are the same road. That may be a separate alley between two buildings. But we eventually managed to get a complete connected road system, and then we could deal with putting the population together. That involved using the census information, such as the number of, I need to describe the census information. The census data is organized around our political organizations, like states and counties, but then within a county, it goes down to tracts, TRACTS. And those have approximately 4,000 people, 2,000 to 6,000 people. But we're using the data that's available down that fine a resolution to synthesize our population. At the tract level, we know how many homes there are, how many businesses there are, how many people there are by age, by sex, and how many households there are. And so we can generate, we know how many homes, so we know how many households there are. We can take the population numbers and generate households, assembling them from the generated male, female of appropriate ages, and create those individuals, put them into relationships as a household, and then populate the household locations on the road network, as well as assign them to the local schools. And the tract level information connects where people work at the tract level, where whatever cities, whatever community they're in, and the tract level that their office is in, where they work. So we know the commuting distances approximately from somebody who works in this specific tract and where they live, and therefore have to commute between those two. So, starting with our road network, we added in the homes and the workplaces and the schools to build our synthetic population. This picture, let me go back one slide. This is what we started with, a nice rectangular shape, and we filled in our population of approximately 23 million. We synthesized their homes, their workplaces, their schools, etc., And when we got into the details, we had done that at the county level, as intentionally to do it at the county level, and that wasn't precise enough for our future work because we needed to be able to have them move between specific tracks for commuting purposes, and because it would be difficult to explain the people. So we now synthesize the people at the tract level and at the one-to-one level at the tract level. And so it turns out the 2010 census data has some bad data. In the 5,500 tracts that are part of this red area, this red box, there are approximately 24 tracts that had bad data. And what I mean by having bad data was that their total number of households didn't match the number of people they had, or the number of households and the number of people didn't match. There were inconsistencies in the data. And I show you this to show you how big some of the tracts are. Each of those red marks, areas, is an individual tract. So on Long Island, on the Atlantic side, there is a relatively large tract, but there's only approximately 4,000 people living there. When you see some of the red spots in closer to New York City proper, you can see that they're smaller tracts, and they also have some problems with the quality of the data. To put this in context, though, if we ignore those tracts, we are still far better than 99% of the individuals in the entire region are being represented. Because this is what the plot looks like of the good tracts and the population that have been synthesized versus the bad tracts. You could say that we're better than ivory soap. We're better than 99.44% pure. Okay, moving on. We took our synthesized population and compared it as best we could back to other sources. So one thing we could do is take our randomly generated synthesized population and compare it to the census data, which is where it came from, so that's not going to be terribly surprising. But another organization sponsored by NIH has also generated synthetic populations, and we could compare ours to theirs on a tract-by-tract level and see how they compare so that we could validate our results. And here's a couple of charts on the quality of those results. There's 4 basic measures that are available at each of the tract levels: the average family size, the average household size, the number of households that have people under the age of 18, minors, and the number of households who have seniors over 65. And you can see that there's a couple where we had data points that were off by a factor of 8. The population was 8 times off the number of households with seniors. We have since reduced that, but I need to point out that we learned something about the census information that was somewhat of a surprise to us, and that is that census information is not just how many people live there, it's how many people are at a location on April 15th, 2010, or April 15th of each decade, which means that they actually did record some people living in Central Park of New York, some homeless folks living in Central Park. They also list all the college-age students where they are on April 15th. So we have some high-density college-age kids in some of the tracts that have universities or colleges. And where a census tract has some old folks' homes, we also are a little off in our numbers of where they were versus the thumb rules that we were using for synthesizing households and distributing the people across those households. So since this was done, we have improved our thumb rules for synthesizing the populations, and we are not as wildly off. We're down at less than a 400% error on any of these four measures, and all the measures are much better in particular. So this other plot is now the comparison of our data to the it's the same kind of thing. This is the plot is against each tract, and you can see there are a couple of specific tracts that are off for specific measures of households with minors and households with seniors. But we know where they are, and we could deal with them if we got to dealing with that level of precision, granularity. And here's another plot, similarly comparing our data to the census information. And now this plot is showing the distribution of people, of the students, minors, and the school systems. The census information doesn't have information on school systems. We went to appropriate sources to get where the schools are actually located in our region, and we synthesized the population by sending the students to their nearest schools of all three categories of elementary, middle schools, and high schools. And this is just a plot to show that the students are appropriately commuting to their reasonably nearby schools. Then we also synthesized social networks. And this is a depiction of the social networks associated with a single tract. So there's approximately 4,000 dots on the screen, and we highlight one household in red, and that household is a synthesized 57-year-old male and a 56-year-old female that have two children, a 16-year-old female and a 15-year-old male, and then their social networks associated with work. Apparently for this household, the male works outside the home and works with a group of people that are 70 to 57 years old, including a 77-year-old, but they have a social network associated with work. The mother apparently does not work outside the home, but each of the children have a circle of friends. In our random selection, this 16-year-old student, female student, if you notice, has all male friends. So our synthesis may not be terribly off. We also synthesized the patterns of life to address their regular behavior. And so we assigned each of our households a normal pattern of possible arrangements. So on the first line, it's showing a single female, I believe, who starts the day, any given day, midnight, at home, commutes to what looks like a factory, and then eventually later drives back home and spends the rest of the evening at home. The second one is a single father with a child who takes the child to daycare and then goes to work, then picks the child up from daycare and goes home. The next couple appears to be retired. They are at home all day. The next one is working a later shift, an abnormal shift, which is approximately 12 to 15% of the people in the New York area do. And so we have this pattern of their commuting, which is a little different. But we've represented several different types of household commuting patterns based on their population and their demographics, their age, their family makeup, and where the tracks where they live and where they actually commute to on a normal basis. So this next image is a synthesis of their commuting pattern. The green line is the number of agents at home. The pink line is the number of people at work, and you can see the morning rush hour and the afternoon rush hour on each of these first couple of days leading up to the nuclear WMD event going off on the third day. shortly after everybody gets to work. Well, not quite everybody got to work that day. But we demonstrated the routine patterns, and we did that last year, and then this year, or the year before, and then in the most recent year, we've been trying to represent their reaction. In the meantime, in between those two, we had modeled the single shift of everybody working the same worked hours and had them all commuting together. We can also represent their three-shift behavior, and this has a majority of people working during the day and some people working a shift, an evening shift, and then some people working an overnight shift. These are options that we can explore with our model, and the system behaves as we expect. And so now we also, this last year, added the synthesized nuclear weapons effects. And unlike those in the background that in the audience on our webinar with us, we are dealing with a no notice. You know too much about this, so I'm going to describe how we synthesized it. We modeled a small nuclear weapon intentionally, partly because we thought that if the purpose of the weapon is terrorism, having one weapon, you know which way to run. If there are two weapons, you don't. So we are exploring that we may want to go in that direction eventually. But we are also simplifying our task by starting with a no-notice event. So people are not evacuating early. They are not stockpiling supplies. They are surprised. Our model allows us to put the weapon anywhere in our region and make it of any yield we would like, but we are simulating a ground burst for our purposes, partly because we do want to get to modeling the fallout and the reaction. And weapons effects are normally described in physics terms, but because we are trying to understand the human behavior, I'm not as concerned about the amount of energy deposited at any specific distance. I want to know what the effects are on the humans. And so we picked 3 radii to use, a short radius, effectively the fireball distance, where we say all the people are killed instantly, and there's no survivors from that short radius. We deal with a second radius, which is effectively these people are mortally wounded, either due to falling buildings, blast effects, where 90% or so of the damage is on humans is as a result of routine non-nuclear blast effects. The point is that it's a blast, not that it's a nuclear blast. And fires resulting from the weapon and from radiation. Those folks, the majority of them, will die over the next 48 hours or so. And so we model they're not instantly killed. That was in the first radius, but these people are dying off basically exponentially over the next 48 hours or so. And then we have a third radius, which is they're injured, but they will probably survive. They're in a rubble field area, but they are able to move. So we are dealing with people evacuating buildings and trying to escape the area. And outside of that third radius, we're presuming that the people are uninjured and still have access to road systems and transportation. That's not quite the normal physics definitions of 3, but they're comparable. We are also only using Glaston and Dunland, 1977, as the publicly available reference for the effects of the nuclear weapons, blast, fire, structural damage, and radiation effects. So here are some images of our model. Our technology available here does not include me being able to show you some movies, but I will show you some images from this. And so this is our regional area. These are the people at work. The color codes are that the green are the people who are unaffected, basically by the weapon. The blue, scattered all over the place, are representing some first responders that are part of the population. And then in the damaged area, we have the three rings. It's difficult to see, but there are small dots in the center for the people who are killed instantly. There is a red collection of agents who are mortally injured, and there is an orange, tried to be orange, to demonstrate where the people were that were injured. And all of that is based on their distance from ground zero. And that's the big picture. That gives you an idea of what 10 kilotons does in downtown New York, or just a little bit south of the Central Park. And I think I could go back. Nope. Okay. When I get to talking about reactions, I will get to showing that. Okay. So we had agents in three different regions. The first zone, they're all dead. The second agent in the second zone, they're basically dying over the next 48 hours or so. And then the last region, they're fleeing either instantly, or they are, when they eventually find out that there was a nuclear weapon in New York, they may decide to go home, as people did on 9/11. So we are modeling that the victims inside that are injured, either mortally or survivably, that they are moving on foot at different speeds based on the significance of their injury. And we have a range of levels of injury for our agents, and therefore their rate of movement. And they're all tending to move away from ground zero for this single weapon representation. And the first responders are doing the opposite. They're moving toward ground zero location, and they will eventually be interacting with the people that they find on their way who need assistance. So we model our agents with decision trees. These are basically fast and frugal decision trees from the folks at the Max Planck Institute. It's not the same as simple rules that don't have any context. These have context of previous rules that would have been considered, and they are intended to be simple, to be executably efficient, and still represent people's behavior. As an example of how fast and frugal decision trees are useful, they've modeled the decision making of a couple of magistrates in the UK on their decisions on whether or not to grant bail. When asked of the magistrates what they consider, their answer was, of course, they consider everything about the accused. But with a very simple decision tree that only asked 3 questions, they could represent over 90% of the decisions that they made. And that's not a general 90%. That's 92 and 94% for the 2 different courtrooms. And the questions were not identical in the 2 courtrooms, but 2 of the 3 questions were the same. They were just in a different order. And the reason I bring that up is that this fast and frugal decision tree is useful to get the vast majority of the behavior. When you're modeling people, if you can get 80% validity between what you think people are doing and what they actually did, you're doing well. To get 90% is almost hard to believe. But we're trying to use this decision tree approach to get to this. So we are representing a naive victim as the first thing they're dealing with is whether or not they are mobile. And if they're still in the rubble, they may not be able to move at all. If they're outside of rubble, they may. So if they can't move, we will have them call for help to alert a first responder or even other injured people who might be able to help them. If they're still in danger or they feel they're in danger, they should be moving away from ground zero. If there's aid nearby, they should move to the aid. If there isn't aid nearby, they should be looking for aid. So that's our modeling of a simple naive victim. If we want to explore the CDC's advice and good sense that if they're inside and there's fallout involved, they probably should not go outside and pick up more radiation, and they should try to get to the best shielded area within their buildings. That the decision tree that a trained victim, knowledgeable victim might use would be a little bit different. So we have the same thing. If they can't move, they would call for help. If they're outside, they would shelter indoors. If there are injured people nearby, they might provide aid, and they're supposed to wait for further instructions before they consider evacuating or fleeing the area. And we have a similar simple decision tree for first responders. If there's injured nearby, they want to provide aid. If there aren't, they want to head, and they're outside a high radiation area, by some definition, they would want to move closer in and to find other victims, and they may eventually want to go to an aid station. In the very first reaction time to a nuclear WMD event, we're presuming for the first hour or so that it isn't yet organized. So there are plans to have relief stations, first response centers established around a disaster, and in our first hour or so, we're not counting on that, and we will get to modeling that a little bit later. So I showed you this picture as an image, and now I can zoom in and show you some of the details with smaller dots, so that you can see that in this one you can see the circles for the people that are killed instantly, those that are fatally injured, those that are injured, and there are also the blue first responders working their way inbound, and there are some gray agents. This is the gray agents are the people who are blocked at the moment from what they are trying to do. You can see some along the East River, I believe it's the East River on the right-hand side, that they've reached the water and they are not allowed to walk on water. And the other gray that are inside are those who tried to commute through the rubble area, and we have stopped their vehicles and frozen them there. You can also see a little bit of a separation in the orange-colored agents, that there are some that are farther away than the others. That's an indication of their general health being a little bit better. They can move a little bit faster. But gives you an idea of the level of detail of the modeling behavior that we can represent. So to get toward characterizing the agents and their reaction, a couple of points. We don't want to just dump numbers on our sponsor of people and what they're doing, but we want to collect information. It's sort of, we've got to develop the appropriate statistical methods to present our information of what people are doing. So we're going to categorize people's reaction and keep track of the number of people who are doing different activities. And there's going to be a relatively high variety of those kinds of reactions. And here is the image, the counts for a single run of an agent-based model with approximately 23,000 agents represented 1/10 of 1% of our population. And they started off at midnight with everybody at home. So we're dealing with one shift in this simulation. And then they commuted to work in the morning after 5 o'clock. And so everybody of the 7,500 who were working were at work. And at 10 a.m. is when the weapon went off. And we have several different colored lines. So let me go through some of those. So the red line are all the people who are in the zone 1 and zone 2 and zone 3. Those are the people who are fleeing the weapon. They are on foot and moving away from ground zero. They're no longer working. Their buildings have been destroyed or severely damaged, so we didn't consider them as agents at work. The black line are the people who were killed, who were inside the first zone, and people who are dying over the first 60 minutes after the weapon went off. I should have mentioned probably earlier that we are modeling our agents not just at the individual level, but at a 1-minute time step, because we can, and because there's only 1,440 minutes in a day, and 1 minute seemed like a reasonable granularity for their movement, both in normal commuting and if they're moving on foot and reacting to a nuclear weapon. So the scale on the x-axis is in minutes. I've indicated midnight and 5 a.m. at 300 minutes and 10 o'clock at 600 minutes. And you see the curves coming up. The black line and red line I've described, they're the dead and dying. The orange line are people who are able to commute normally home, so they're outside of the immediate damage area and they're commuting home, and some of them get home fairly quickly. They have short commutes. And the gray line are the people who have tried to commute through the damaged area or have tried to walk over water. And we're going to deal with that representation and the traffic jams that are produced as a result of that. But this simulation only is running for 1 hour after the initial weapon goes off. But one of the significant points of an agent-based model is that because you're modeling all the individuals and having all of them make decisions and interact with each other, you're representing a projected future with a whole lot of assumptions and probabilities involved. So a single run is potentially not representative. We could have chaotic behavior and wild and strange things occurring. So I'm going to show you a plot of 25 runs. This is the same information, or most of the same information, plotted from the results of 25 runs. And you see that the lines are relatively thin when everybody is doing the same thing. So there's some stochasticity in their commutes, and so the numbers of people at home and at work are spread a little bit, but the law of large numbers is coming to our rescue and making them behave. But then after the weapon goes off, since their probability, we know where they are at time zero, and so we can predict how many are killed instantly. But how many die over the next 48 hours is a random phenomenon. When people find out about the weapon's discharge, and find their way out of the rubble and commuting home is right now relatively probabilistic, stochastic in nature. And so you see what those 25 runs look like. Our model is not very noisy, especially given that we're dealing with only a single shift, people aren't already at home, things like that. But you can see about what the spread looks like. And if this holds, we hope to be able to come up with a reduced order model so that we don't actually need to run large simulations with millions of agents to have a reasonable representation of what the overall effects are. So that is how we're characterizing the reaction to the nuclear weapons, nuclear WMD event. So we have described our process and results so far in publications and presentations. We've made presentations to the Defense Threat Reduction Agency a couple of times. We've taken our modeling approach and representations and our methodology to anthropologists, and specifically disaster anthropologists. That's not a specific organization, but we have organized workshops on disaster response. And there are anthropologists who study disasters. And we've been to geographers and demonstrated our geographic information system and our tracking of individuals and their behaviors. We present to other computational social scientists to make sure our methods are conforming with the acceptable science approach. And we've presented in academic seminars and our classes and things like that. And the last topic is our progress plans and future work. So we've demonstrated and benchmarked and verified and validated our population synthesis and our social networks, their distribution, their characteristics, and our methodology for representing our agents. And we've done that with parts of the data set getting toward the 23 million. We haven't done many runs with 23 million. That takes several days, and we just haven't had that many runs yet. We've integrated our households and social networks so that we can represent them explicitly in our system. We are looking forward to modeling the formation of cohorts of people leaving buildings and providing assistance to each other as they are escaping the area before they get assistance from outside or first responders start to show up. We've generated reasonable models of New York City's commuting with populations up to 260,000 agents. And we've described our detonations and populations running our experiments so far with 23,000 agents. So in the future, we're going to refine the modeling fidelity, improve include more specific health effects and first aid response and assistance to blast effects of our agents and fire effects. We're going to be modeling the communications. We know people want to reach their loved ones and communicate and check their status. And we're going to be dealing with an EMP, which I believe is another bullet later, to complicate our model. We're going to also deal with the damage to our road networks and communication paths that are going to complicate the reaction of our agents. And as I said, we're going to include some electromagnetic pulse effects and effects on the communications, and do what we can to validate our model against other scenarios which are comparable. No-notice events such as earthquakes, fires, explosions, but not other nuclear weapons other than Nagasaki and Hiroshima. But we can compare people's reactions and represent them appropriately in our model to confirm that our model is behaving reasonably. So we've been addressing some resource challenges, we've been characterizing the population's reaction, and we're going to be enhancing the model's fidelity. And so we have some time, and I'll look at dealing with the questions. So there are questions on here, and there are more coming in. So let me see what I can do to make sense of these. Does your current model take into consideration the effects on transportation and potential evacuation routes? We do. In general, the answer is yes, but we're going to do more with that. Right now, the when you talk about potential evacuation routes, that's more than the first hour. So we haven't gotten that far in our simulation to deal with more than the normal commuting evacuation routes. We will get to that. The second question is, what kind of weapon yield are you referring to? We're not looking specifically at a 10 kiloton national planning scenario number one. We are modeling the effects and how we think the population will react, as opposed to how they're intended to react, if I characterize that appropriately. What language? I'm sorry, I didn't mention that. The model is written in Java using the Mason agent-based modeling framework. The Mason agent-based modeling framework is a system openly available, developed by our computer science department, colleagues in the building next door. It's available for free, and our model runs within that environment. So it's a Java program that is running with all the agents simulated. What are your next steps? Are you planning to do further research and updating the model? Yes, we are continuing. We have at least 2 more years of funding, and if people wanted to look at specific scenarios, we could certainly consider that. Which ABS platform are you using? I've now answered that. That's Mason. We did some prototyping in NetLogo, which is a very simple agent-based modeling environment used all the way down into elementary schools, but it is useful for quick tests of concepts. But the bulk of our work is in the Mason system. There are other environments for developing agent-based models, but we are most familiar with Mason. 2, it's an industrial scale system. It is fast, it is efficient, and it can deal with the size of the environment that we're dealing with. The last question I see at the moment is, are there any plans for how these results could be used to improve population survivability? We are certainly considering things like that. It might be interesting to consider some what-ifs when we get to a more complete picture of people's reactions a little longer than an hour afterwards. We will be able to model things like, what if people do not all shelter in place because they didn't get the message from the CDC or other agencies that they should stay in place? And what if the most significant impact is the damages of the physical damage, the blast effects and the fire effects, and what we need is to pre-position first aid materials so that we can save the people who are savable in the first hour or so. But yes, we are certainly hoping to get to the point where we can explore different policy options. There is a PhD student associated with our project who is exploring how close to a nuclear weapons disaster should you set up first response facilities, and she's addressing modeling first responders' hesitation to provide assistance to people who have been exposed to radiation. We have a lot of training to do, apparently. So that seems like that's about it. Thank you very much, and you're welcome to contact me if you have any other further questions. Thank you.
Dr. Kennedy, thank you so much. As you can see on the slide here, we have a survey available to, and we would ask that you fill out if you also have any recommendations for future topics that you'd be interested in hearing, or if you have a future topic that you'd be interested in presenting, we would welcome those here. Thank you again, Dr. Kennedy. Thank you all for those that attended. For additional information about this topic or any other topics, please please feel free to visit our website at hdiac.org. Thank you.